Good afternoon, viewers. Myself is Dr. Sumit Banerjee, the Professor of Mathematics from the Department of Mathematics and Computer Science. The topic of my today's presentation is analysis of signal processing embedded with the Fourier transform. In my presentation, I'll put more emphasis on the Fourier transform part and we'll discuss the various characteristics of signal processing, and we'll try to show how Fourier transform can be used in an effective manner to analyze the signal processing in an easy manner. And finally, I will establish the finding of this research through those characteristics. The objective of this presentation is that how the easy manner Fourier transform can be used to retain the quality of the signal and extracting the maximum information the signal is carried out. So let's start from the basics and background of the signal. What does the signal means mathematically? Mathematically, signal is nothing but it is a function or mapping. It's just transforming this information about any phenomena. Any quantity that can vary over space or time can be used as a signal to share the messages between the observer. Signal processing involves the transmitting the data in a way that allow us to analyze and interpreting the signal in such a manner that is not possible via direct observations. The signal processing involves that transmitting, interpreting, and manipulating the analog and digital signal. Some example of the system that manipulate signals are speech recognition, video streaming, cellular networks, and medical scans such as MRI and CT scans. There we can use the signal processing. And in IEEE transactions, we using the different kind of signal processing like the audio signal processing, video signal processing, images, radar, and sonar. IEEE transaction is basically it is a scientific journal discussing all aspects of the computer design. So in my today's presentation, I'll discuss mainly the signal system and the transform. Signal is basically a function of mapping. For every input signal, there is an output representation. Like see every input, every signal having every input function having the output. So it can form either directly the one-to-one mapping, or it may form the many-to-one mapping. It may form the one-to-one or many-to-one mapping from the input set to the output set. Audio signal we are considering as a one-dimensional function with respect to time. Since audio signal is mainly depends on its wavelength, and wavelength is a length basically, and it is length is one-dimensional. That's why audio signal is considered as a one-dimensional function. Whereas when we're talking about the images, image is considered as a two-dimensional function because it takes the two input variable and corresponds to a single output which is represent the height of the image. Like if we take the two different input variable and they will correspond to a single output that represent the height of the image. Signal we are categorizing in the two types. One is the analog signal, another is the digital signal. Analog signal processing is for the signal that have not been discretized in the legacy radio, telephone, radar, and the television system. Whereas in the digital signal processing is the processing of digitized the discrete time sampled signal. Here the entire population of the signal we are not considering, we are taking the sample part of the signal. And here we are using the Fourier transform to convert the sample functions from the original time domain to the frequency domain. So since in my presentation I'll discuss the various characteristic of the signal processing. The first characteristic is the signal. Signal is a function. When signal travel, it requires the space to travel, and it will travel up to a certain time. So here the time and space are the two universal independent variable. So signal can be considered as the function of time and space. So when signal will be represented in a frequency domain, so it will be very easy to analyze your signal. And in a frequency domain, several operations we can perform to eliminate the unnecessary frequencies. Like generally, the low frequency component is represent the overall space of the signal, and high frequency component are the cost due to the noise or presence of edges in the image. To remove the noise, high frequency component need to be reduced, and to sharpen the image, high frequency component need to be emphasized. Here in this diagram, we can show I am talking about that in the signal processing, we are changing the domain from the time domain to the frequency domain. So what is the need to change the time domain to the frequency domain? So from this diagram, I can ensuring this one. Like here in the left hand side the diagram, we are like here in the left hand side of the diagram, if we take any wave function, then the corresponding the diagram in the time domain will be like this. But if you convert the domain into frequency domain, we're going to get one bar diagram. So bar diagram is much more easier to analyze than this kind of the wave function. So if we add the two wave function in the time domain, then the corresponding function will be this kind of nature in the time domain. But corresponding function, sum of the wave function in the frequency domain will going to get two bar diagram, which is much more easier to analyze. But sometimes we can get some irregular shaped signal, like in the space or from the another planet. Suppose some signal is coming, that is an irregular shaped signal. We will not understand that the signal is the sum of which basic wave function. On that occasion, what we'll do on that occasion, we using the Fourier transform to decompose this irregular shape of function to the some known phase of the wave function. So that way also the Fourier transform is the useful tool to analyze the signal processing. Now, in case of the image processing, what we do in image processing, we are converting the signal from the spatial domain to the frequency domain. Spatial domain is the combination of the gray level and the brightness. It is a continuous medium actually. So, what does the Fourier transform do in the image processing? In image processing, Fourier transform is mainly giving the direction of the variation. Like for example, here in this first diagram, if you do the vertically, if you see there is no changes in the pattern actually. The pattern is like the same. Here also the blank space is there is no changes in the pattern. Here also there is no changes in the pattern. But if you consider in the horizontal direction, so here some pattern is there, here some blank is there, and here some pattern is there. That means the horizontal direction, some changes, variation of changes you can find in horizontal direction. So here the Fourier transform will give this variation of the direction in horizontal way. Similarly, in the next diagram, the vertical way, the variation of the direction we will get. Like sometimes if some script is there, suppose from another planet they are sending some messages. So how will come to know that is giving some messages actually? Some messages is there. If some scripts is there, so generally in a paragraph we are writing one line, then we keeping some gap, then we writing the next line. So and every time we maintaining the same gap. So that means here variation will come in the vertical direction like that. So here the Fourier transform will give us the idea that the variation is coming in which direction. Now how the Fourier got the idea that to express any kind of function in terms of the sinusoid waves, how he got the idea first. So first he observed that when the polynomial of the different degrees, if we plot the graph, here you can observe that here all the even degree polynomial, if you draw the graph, so all the graph of the even degree polynomial are just like the symmetric about the vertical axis. Similarly, if you draw the graph of all odd degree polynomial, then these are the reflection about the horizontal axis and then vertical axis. Similar nature he found in the cosine function and the sine function. Cosine function also it is a symmetric about the vertical axis, and sine function is also it is a reflection about the horizontal axis first, then vertical axis. So from here only he got first idea that any polynomial of any even degree or odd degree can be expressed in the sinusoid waves. And then he established this Fourier transform and the Fourier series.